In this video, we'll discuss about how to derive barrier potential in a PN junction, and we also discuss about at the junction potential what is the width of depletion layer. From Gauss law in electrostatics, we know the surface integral or the flux enclosed by the closed surface is equal to 1 by epsilon 0 times the charge enclosed by the surface. And if you use Gauss divergence theorem, the surface integral can be changed into volume integral, and applying Gauss divergence theorem, you can write del dot E equal to rho divided by epsilon 0, and this is the differential form of Gauss law. And if you consider one-dimensional electric field, that is field along, suppose I have taken here field along x-axis, then the differential form can be written as derivative of u with respect to x, that is equal to rho divided by epsilon naught. And here rho is the volume density of charge. But we know that electric field intensity is equal to negative of the potential gradient. So if you write E is equal to minus dv by dx, that will be equal to second derivative of potential with respect to x, that will be equal to minus rho divided by epsilon naught. Here epsilon is the permittivity of the medium. If you take permittivity of empty space, then you write this equation 1, and if you write permittivity of the medium, then you replace epsilon naught by epsilon. So the equation will be equal to second derivative of potential with respect to x, that is equal to minus rho divided by epsilon. Since we are considering the PN junction and it has a medium, so you take epsilon instead of epsilon naught. And here you have taken the concentration of holes and electrons in the depletion region is negligible. If you take concentration of holes and electrons in the depletion layer is negligible, then you can draw this graph, that is this is the x-axis and this is the y-axis, and up to x1 you have the region N, that is the region for the N super semiconductor, and up to the length minus x2 you have P region, that is P type superconductor, and this is your PN junction. And in the y-axis we have taken the volume density of charge, and up to this, if is the electronic charge, then, and I have taken here Nd is the density of ionized donor atoms which extends to x1, then this is your E into Nd, and if you take Na as the density of ionized acceptor atoms which extends up to minus x2, then this will be equal to minus E into Na. And here I have taken the N region is extend more in comparison to the P region, that is x1 is greater than x2. So if you replace the volume density rho divided by E into Nd, that is density of ionized donor atoms, in equation 2 you substitute E into Nd, in place of rho you substitute E into Nd, then the equation will be for N region, the equation will be derivative of potential with respect to x, that is equal to minus E into Nd divided by epsilon, and here the value of x extend from 0 to x1. Similarly for P region, from equation 2 if you replace rho divided by E into Na, that will be equal to derivative of second derivative of potential with respect to x, that is equal to E into Na divided by epsilon, and here x value extend from minus x2 to 0. Now we will derive the expression for the variation of potential across the depletion region. To find out the potential or variation of potential across the depletion region, you have to integrate equation 3 and equation 4. So for n region, if you integrate the equation 3 for n region, it will be equal to derivative of v with respect to x, that will be equal to minus e into n d divided by epsilon into x plus a constant of integration, because if it is indefinite integral. Similarly for p region, you have dv by dx or derivative of v with respect to x, e into na divided by epsilon into x plus c2, where c1 and c2 are constants, and the value of these constants can be found out from boundary conditions. So this is the graph for the variation of potential with distance or with length. In the x-axis you have length x, in the y-axis you have potential Vx. So from minus x2 to 0, this is your p region, and from 0 to x1, this is your n region, and you see how the potential is varying. And at the boundary, you have two boundaries, one at x1 and another at minus x2. And at x1, the variation of potential or dv, the derivative of potential with respect to x, is equal to 0, because potential is constant at boundaries. So here the potential is constant, and also here the potential is constant. If the potential is constant, its derivative will be equal to 0, because derivative of a constant is equal to 0. So dv by dx or derivative of potential with respect to x at x equal to x1 is equal to 0 here, and also dv by dx at x equal to minus x2 here, it is also equal to 0. So putting these boundary conditions in these two equations, that is equation 5 and equation 6, this equation and this equation, we can find out the value of C1 and C2. So if you put dv by dx at x equal to x1 0, then C1 will be equal to e into nd divided by epsilon into x1. And if you put the second boundary condition dv by dx at x equal to minus x2, which is equal to 0 here, then this will be equal to 0 when x equal to minus x2. So C2 will be equal to plus e n1 e na divided by epsilon into x2. So for region n or n region, C1 is equal to e into nd divided by epsilon into x1, and for p region, C2 is equal to e na divided by epsilon into x2. So from equation 5, that is for the n region, if you substitute the value of C1, then it will be equal to derivative of v with respect to x, that is equal to minus e nd divided by epsilon into x plus e into nd divided by epsilon into x1. And if you integrate both the sides of this equation, then vx or vnx will be equal to minus e into nd divided by 2 epsilon into x square plus e into nd divided by epsilon into x1 into x plus c3. Suppose this is equation number 5.1, and the value of c3 can be found out from the boundary condition. So using the boundary condition, that is, you have to use this boundary condition, that is Vx is equal to Vb at x equal to x1. This boundary condition you have to use. I have taken here two boundary conditions. One boundary condition for the p side, this is for the p side, and this is for the n side. For the n side, the potential is equal to Vb, as I have shown you in the figure. You see this figure, at x equal to x1, the potential is equal to Vb, and at x equal to minus x2, the potential is equal to 0. So you put these boundary conditions to find out the value of the constants C3 and C4. And C3 is the constant to find out the expression for the potential at the n side. This is for the expression for the potential at the n side. So if you calculate or find out this constant C3 by using the boundary condition, then you will find out the expression for the potential for the n side. Similarly, if you find out the constants C4, that is in the for the n side, p side, using this boundary condition, then that will be the expression for the potential for the p side. So here we have we will calculate C3. So using this boundary condition, that is Vx is equal to Vb at x equal to x1. So you put here Vb and x equal to x1. You put here x equal to x1, here also x equal to x1, and calculate C3. Here I have calculated the value of C3 is equal to Vb minus E into Nd x1 square divided by twice epsilon. So now you put the value of C3 here. I have put the value of C3 here in equation 5.1. You see, if you put the value of C3 in 5.1, then you will get the expression for the equation for the potential in the entire n region. So this will be the expression for the potential for the entire n region, and this is equation 5.2, and the value will be equal to, expression for potential will be equal to minus E Nd divided by epsilon into x square by 2 plus x1 square by 2 minus x1 x2 plus Vb. Then now for the P region, we will find out the expression for potential, and from equation 6 we have the expression for potential. We have find out derivative of V with respect to x is equal to E Na divided by epsilon into x plus a C2, and we have found out the value of C2, and if you substitute the value of C2, then this will be E Na divided by epsilon into x2, and you again integrate both the sides. If you integrate both the sides, you will get the expression for the potential for the P side, that is Vpx is equal to E Na divided by twice epsilon x square plus E Na divided by epsilon into x2 into x plus C4, and we have to find out the value of C4 from boundary condition. As I have told you, if you use the boundary condition, that is Vx equal to 0 at x equal to minus x2, then you will get this equation 0 is equal to E Na divided by twice epsilon x square minus E Na divided by epsilon x2 square plus C4, and you calculate the value of C4, E Na divided by twice epsilon into x2 square, and if you put the value of C4 in equation 5.3, you will find out the expression for the potential for the P region, that is Vpx will be equal to E Na divided by epsilon x square by 2 plus x2 square by 2 plus x into x2. So these two equations, this equation gives the expression for the potential in the entire P region. So in equation 5.2, we have find out the equation for the potential for the entire n region, and in equation 5.4 we have found out the equation for the potential for the entire P region. And now we will find out the width of the depletion layer at the junction potential. So at the junction, that is the PN junction, the x value is equal to 0, and the potential for the n region will be equal to the potential of the P region. So Vn0 is equal to Vp0, and at the junction potential we will calculate what will be the width of the depletion layer. So from equation 5.2 and equation 5.4, in equation 5.2, this is your equation 5.2. If here you put x value equal to 0, so the potential will be equal to minus E Nd divided by epsilon into x1 square divided by 2 plus Vb. Okay. Similarly, here you see I have written equation 5.2. Here I have written equation 5.2, and if you put this condition, that is the condition for the junction potential, that is x equal to 0. If you put this condition in equation 5.4, you see this is the equation 5.4. If you put x equal to 0, this will be equal to E into Na divided by epsilon into x2 square divided by 2. This term will be equal to 0 and the potential are equal, that is V n x will be is equal to V px. So you see here I have taken the equation. You see I have taken here this is for the n region at the depletion junction potential, and this is for the p region at the junction potential. So these are two, this will be equal to this. Obeying this condition, you write this equation. So from this you can calculate Vb. So if you calculate Vb, this will be equal to E into Na divided by epsilon into x2 square divided by 2 plus E into Nd divided by epsilon into x1 square by 2. And another thing is, from charge conservation, we know Nd into x1 is equal to Na into x2. So if you take common here, you take common here Na into x2 square. So this term, and also we have taken common E divided by twice epsilon. So E divided by twice epsilon, and you take common here Na into x2 square. So in the bracket you have 1 plus Nd x2 square x1 square divided by Na x2 square. And from this condition, if you put this condition, that is x1 by x2, that is equal to Na divided by Nd. If you put this condition here, x1 square by x2 square will be equal to Na square divided by Nd square, and if you solve it, then you will get E divided by twice epsilon into 1 plus Nd divided by Na. Okay. And this equation, E divided by twice epsilon is into 1 plus Na divided by Nd into Na x2 square. Suppose this is equation number 7. Similarly, if you take common from this equation, if you take common Nd into x1 square, then you will get this equation, equation 8. You have another equation. So one equation for Na x2 square and another equation for Nd x1 square. And from equation 8 you can find out the value of x1. If you take this one to the left side and you find out the value of x1, and from equation 7 you find out the value of x2. You bringing this value to the left hand side, and right you can find out the value of x2. And you see I have calculated it. The value of x1 is equal to 2 epsilon Na Vb divided by E into Na plus Nd into Nd to whole to the power half, from equation 8. And from equation 7, if you solve for x2, that will be equal to 2 epsilon Nd Vb divided by E into Na plus Nd into Na whole to the power half. And here the width of the depletion layer for the asymmetric step junction width, here the junction width is not symmetric. That means x1 value is not equal to x2 value. I have shown you in the diagram that x1 is greater than x2. So for asymmetric step junction width, the total width x will be equal to x0 will be equal to x1 plus x2. You can write the width is equal to w. So w, that is equal to also written as x0, which is equal to x1 plus x2. So if you add x1 plus x2, then w will be equal to 2 epsilon Vb Na plus Nd divided by E into Na Nd to whole to the power half. So this is the expression for the width of the depletion layer, and the step junction width is not symmetric, it is asymmetric. And I have calculated here x1 plus x2, that is the width of the asymmetric step junction. I have calculated it. You calculate yourself. It is very simple. If you find any problem, then you see this calculation. Now let us calculate the width of the depletion layer for symmetric step junction. If the junction is symmetric, then x1 is equal to x2 and you write it x0 divided by 2. And for symmetric step junction, also Na equal to Nd and you take it N. And if you write x1 in place of x1 and x2 in equation 9, this is your equation 9. If you substitute Na equal to N and Nd also equal to N, then the width of the depletion layer for the symmetric step junction, this will be equal to W is equal to 2 into epsilon into Vb into N plus N divided by E into N plus N into N whole to the power half, and 1 N cancel, so that the width will be equal to 4 epsilon Vb divided by E into N whole to the power half. So in this video we have derived three things, that is the derivation for the barrier potential for the entire P region and for the entire N region, and we have also find out the width of the depletion layer for the symmetric step junction and also for the asymmetric step junction.